Hello everyone. If we'll start the class in 5 to 10 minutes. If you have any doubts, you can put your doubts in chat box, or you can just ask your question unmuting yourself. Hello, good evening everyone. Am I audible to you guys? Somebody asked a question about explain the effect of size of coarse aggregate on strength of concrete. So normally if we talk about coarse aggregate, we will check the shape and size both, because what will happen if you have a very large size of coarse aggregate, there are chances of voids happening. So as we study about different type of packing density, like in last lecture we talked about packing density. So very large aggregate with not a good shape, they will cause voids and will affect the packing density of our aggregates. And if we have a smaller size coarse aggregate, then there are chances of a good surface area, and so that's why we have limited our coarse aggregate size to maximum 20 more. If we have a, let's say, 25 or 30 diameter aggregates, there are chances of that aggregate being the weak zone. So we can't guarantee that aggregate will be always the stronger one. There are chances of it become the weak zone, and it can cause more issues. Also itz issues can be there. So there are many factors which are there and can affect the strength or other properties also. So therefore we do this particle packing and everything about aggregates to optimize the aggregate size. Is it okay? Okay. Anybody else who have any doubt? Okay, if there are no doubts, then we will start the session for today. So, good evening, I am Shefali Agarwal, and this is our ninth TA session on the topic of advanced concrete technology. So in as of now we have already talked about what is the how a cement is produced, and what is the composition chemistry and different elements of our cement, like aggregates, admixtures, mineral admixtures, and then how we will do mixed proportioning, and what should be the properties of our fresh concrete. So in this lecture we will talk about hardened concrete. And if we talk about hardened concrete, first thing that came into everyone's mind is the what are the mechanical properties of any concrete. So mechanical properties, now in mechanical properties also we are dividing it to three part further. First is instantaneous or time dependent properties, like strength, stiffness, then creep, shrinkage. Those are the general properties, general mechanical properties of our any concrete system. And next is the, if we talk about strength property itself, then in strength only itself we have many type of strength properties, how our concrete is behaving under compression, tension, pressure, shear or torsion, depending on the application we are using our concrete for. Last thing is about the durability. So durability is as important as we talk about mechanical properties. How? Because it will affect the long term properties of our concrete. So main durability properties which we look into our concrete are permeability and pore structure, freeze thaw resistance, mainly when we are talking about some hilly areas and all, corrosion resistance, and then other small things like alkali silica reaction, carbonation, or any other chemical deterioration. Next thing is about mechanical properties only. The main thing which affect all three type of mechanical properties, let's say durability, strength, or any general properties, is the hydration and how our pore structure is being developed. That will be affecting our further or long term properties. So our initial properties of concrete or initial how it is getting mixed and all will affect our further future properties or our long term properties of the concrete system. So important parameters which we look into our concrete is composition, where we check about paste versus filler, how much we have a paste and how much it is acting as a filler, especially when we are adding some supplementary cementitious material. Then what is the cement type, its composition is different property. Then aggregate properties is roughness, grading, composition, water to cement ratio, water to binder ratio, curing conditions, humidity, air content, temperature. So these are the important parameters which we look into before designing or before thinking about the mechanical properties of the concrete. So if we talk about the first thing, which is the strength of our concrete, what are the various factors which are affecting the strength of our concrete? So if you see here, strength of the concrete, it is depending on the first thing is quality of aggregates. So if what is the surface characteristic of our aggregate, chemical composition, our aggregate should not be too much brittle also. And then what is the concentration, mixed design of our aggregates, particle size, modulus of elasticity. So all this important factor of aggregates will directly or indirectly will affect the strength of our concrete system. So other thing is, first is aggregate, second thing is paste. So we know our concrete mix is made of two component, paste component and aggregate component. When we talk about paste, so our paste properties are affected by the moisture content, how much water to cement ratio is there, then what is the degree of hydration, which will indirectly affect the porosity, and what is the gel structure. Gel structure means CSH, how much CSH is formed, or other hydration product, how they are forming, and this will further depend on the type of cement, age of paste, curing condition, and what are the various type of admixtures which we are using. So end of the day, whatever we have studies before this about the fresh properties or any other thing will affect the hardened property or strength of our concrete system. Okay, next thing is how our strength will be changing with respect to time. So usually when we are calculating our compressive strength, we calculate it as a 28 day strength. Why? Because we assume almost how much percentage of strength is gained at 28 day. Any idea? How much percentage of strength is gained at 28 days?
95.
Correct.
110.
Sorry. So approximately
110, madam.
no, for normal concrete generally 95 to 98 percentage of strength is gained by 28 days. Not it's a long term process, like many people will calculate at 56 days also, 90 days also, but generally if we talk about target strength, almost 98% of target strength is gained at 28 days. So if we see here, so there are different curing condition, and in different curing condition are different type of strength gain is there. So if we talk about our moist cure condition completely, like if we are dipping it in or keeping it in a moist environment for 28 days, it's showing that almost 100% of strength is gained. But if it is in air, after 7 days of moist curing, it is little bit less than 100%. If it is in air after just 3 days of moist curing, it will be more less, and if it is just air curing, normal curing, it will be very less, it won't get 100% of strength. So that's why approximately at 28 days we will have 95 to 98% of strength gain. We usually won't get 100%. This is not our characteristic strength, this will be our target strength. Okay, So next thing about 1 minute. So generally in our concrete, our stress strain curve is almost linear curve, which will after that it will fail. So if we talk about stress strain curve, at almost 30% of stress level there is negligible bond cracks, and when our stress strain within 30 to 50% of stress levels, slowly bond crack will develop, and then there will be a crack in the matrix, and at last moment at 75 to 100% of crack stress, there is a fast growth of matrix crack and your concrete will break. So if we talk about general compressive strength test, sorry, if this is our concave system and if we are applying compressive strength, how will our crack pattern will look like? Mostly in this way, right? If you have seen any lab testing of concrete, it will crack in this way, right? So that thing, I don't know if we have talked about it. Shape factor of our concrete system also will affect the type of your strength value. So if I am using a cube system, 100 mm or 150 mm cube system, my load this will look like this. So your L by D ratio in this case is 1. So your deformation will be in this way. But if we are using cylindrical system, in that in that case your L by D, it will be 150 mm, or sorry, 100 mm by 200 mm. So your L by D ratio will be approximately equal to 2. In that case your deform shape and your strength value will be very much different than your cube value. Okay, so it's not just the concrete mix design which is affecting our strength property or resultant strength, it will be the shape of your testing system also. So if it same way, if here you see stress versus strain curve, initially your stress is directly proportional to strain. At one point when you crack start, or it will crack start propagating, at that point there is a sudden decrease. So it won't be like your steel system where you will get this kind of curve approximately. So there won't be any elasticity behavior. It is a brittle material, so once cracks start propagating, it will suddenly fail at approximately at 0.004 strain. You will have this kind of failure structure. Okay, so same thing is being shown here. If you see at the initial linear stage, what will happen? There will be a small cracking along the ITZ area, interfacial transition zone area only, and then what happens, slowly that ITZ cracks will become more severe, and then they start joining with each other, and once it they start joining with each other, and once it is fully joined crack, it will your concrete will break, and you will, after post peak, you will have this kind of structure. Your cracks will be fully open. Similar kind of thing is shown here. It's instead of stress versus strain curve, we are seeing load versus displacement curve. So even in load versus displacement, again in linear region, small cracks got increased. At peak point there is a crack, and in crack what is showing, if you are unloading it, it will come back to linear region. But if you are loading it, keep on loading it, it will go in this direction, like in further in lower direction, but won't be in a linear way. Okay, so again here it's showing stress strain curve of different type of concrete. So two type of concrete is showing: normal weight concrete and lightweight concrete. What is the difference between these two type of curves is your peak point in lightweight concrete is much farther away than in your normal concrete, right? And this is your stress strain response of different type of under different type of loading. So if you see here, uh, this is in strength in MPa and here strength is in PSI. So as the strength increases, the stress strain curve, it show higher elastic modulus. So as your strength is increasing at different strength value, these curves are there, your value of modulus of elasticity is also increasing. And the only difference is when you talk about this peak point, also this peak point will become more sharper. So if let's say this is your 20 MPa concrete and this one is your 80 MPa concrete. So if you compare your 20 and 80 MPa concrete, your elastic modulus is less, but you have a very your concrete won't fail suddenly. Your peak is very it's not much sharp, but when you compare it with the higher strength concrete, you will have a higher linear region. Your elastic modulus will be higher, but your peak will be very sharp and will have a sharper descent also. So after crack it will suddenly decrease, but in this case after crack it will go linearly. Okay. So this is what it is about post peak behavior. So this is a lower strength concrete, it is going smoothly, and higher strength concrete, what will happen once it reach a peak, there is a sudden decrease in stress condition. Or other thing is, if you are changing the type of concrete, instead of using your normal concrete, if you are changing your type of concrete, what will happen, this is your normal concrete curve. If you are adding some fibers to it, so what fibers we are doing, they will stop the crack from opening. So in that case what will happen, your post peak behavior will change in this way. So if we see this stress strain curve normally, in brittle case what will happen, once it reach at peak position, it will suddenly fail. If it is coming in this direction, we are calling it as strain softening. If it is going in this direction, strain hardening, as we see in our steel system. And if it is going like this and then straight, it is elastic plastic region. So how we are calculating this post peak behavior of our concrete system? Usually when we are doing testing, what we are doing, whenever this will break, we will stop our testing, right? Whenever we crack is initiated. So there are different type of models through which we can obtain our post peak behavior. First model is composite model. So in composite model, different type of is showing. For composite, it will come as stress versus deflection curve we will get. So in composite we will get this kind of curve. In term of steel you will get a straight curve, and in term of concrete you will get a curve like this. So all are stress versus deflection curve. So if we talk about if we are calculating in concrete only, this is our composite system which will have both steel and concrete. So we are putting both steel and concrete under compression, and then we are getting its stress versus deflection curve. For then only for steel we are calculating this curve. So subtracting these two curves, you will get the deflection curve, stress versus deflection curve for the concrete system, and then you are getting this post peak behavior. Other way is using closed loop testing system with displacement control. So in this in this method we are controlling our displacement, keeping our displacement constant instead of keeping our loading constant. So what we are doing, So this is a load cell, and we are calculating same thing. We are providing compressive strength to a concrete system and collecting the data at every single point of loading condition. So at every loading condition we will calculate the displacement value. So our displacement is in control position, we are giving our displacement, and in that case we will calculate our post peak behavior. So if it see what are the different loading situation in our concrete system. First is uniaxial compression test. So in that we are providing load from one end, from here to here. Second is biaxial compression. Biaxial compression means providing loading from two ends, like from top and bottom and in the sideway. Third is compression and tension. In that case what will happen, two ends will be in compression and two will be in tension. And another one is biaxial tension. In that way both are in tension condition, and your concrete will fail in a sudden way. It will have full crack and it will come up in two pieces that way. And last and important is triaxial compression. In that case we are applying loading in all three directions. So firstly, if we talk about uniaxial loading, what is happening in uniaxial loading? Your failure planes are the planes of principal tensile strain. So if you see here in uniaxial compression testing, what will happen, your failure planes are in direction of your loading condition. So it will be in other planes of principal tensile strain, which are parallel to the direction of applied load. In the case of uniaxial tensile loading, so that was compression. In case of tensile loading, what is happening, your failure plane is against the plane of maximum principal strain, which is perpendicular to the applied load. So if it is in compression, your failure plane will be in this direction. If it is in tension, your failure plane will be in this direction. So it will be perpendicular to the direction of your, like in this case, if it is a tension, your failure plane will be perpendicular to the direction of loading. Next is about biaxial loading. In biaxial loading, what is happening? First is in compression. In compression, your failure planes are the planes of maximum principal tensile strain, which are parallel to both the applied principal compressive stresses. Such loading causes an increase in overall strength. This increase is especially high if end restraint also exists. The strength increase can be high as 27%. So if we are talking about biaxial loading, if we are loading it in compressing it in both direction, what will happen, you are actually making your concrete system more compact. So if your concrete is getting more compact, your strength value will initially increase and your failure planes are parallel to both direction. And in case of biaxial compression and
Madam, presentation not showing. Hello, madam, your presentation not showing.
it's not visible. One,
Yes, madam, not visible.
I'll try again. Is it visible now?
Yes, madam.
Okay. So in case when we are applying both compression and tension in biaxial direction, what will happen? Your overall strength will reduce because of tensile strains, and failure plane will be perpendicular to the maximum principal tensile stress condition. So if we see from this figure, if we are applying both compression and tension, in this direction it is compression, in this direction it is tension. So what will happen, your strength will actually reduce because of the additional tensile forces, and your failure plane will always be in the direction of your principal compressive strength principal compressive stresses direction. uh, next thing is about if we have biaxial tension. So it is not given in the slide. So if you have biaxial tension, if you are applying tension in both direction, or even if it is a uniaxial tension, what will happen? Your failure will be in the direction perpendicular to your tension plane. And if it is biaxial also, then also your failure plane will be in the perpendicular direction of any one of the loading condition, loading plane. So last is triaxial loading. So in triaxial compressive loading, it drastically increases the strength of concrete. So same concept. If you are compressing anything in from all direction, you are actually reducing the pores or voids in the concrete system. So it will increase the strength of the concrete in a longer term. So the tensile strains generated are overcome by the compressive stresses. In effect, the specimen is held together and tensile cracking is prevented. Thus, the failure in triaxial loading could occur by pure case of compression. The increase in strength is higher for low strength concrete. More failure envelope is generated for concretes of different strength. The maximum shear strain at failure according to this envelope is equal to the half the difference between maximum and minimum. So what it is trying to say is, when you have let's say we 1 minute, let's see from okay, if this is your stress strain curve, this is your low strength concrete, this is your high strength concrete. So what we are telling, when we are applying triaxial loading, there is an increase in strength value, and that increase in strength value will be more in lower strength concrete as compared to in higher strength concrete. Why it will be like that? If you see here, if I am applying triaxial loading, you in lower strength concrete you will have chances of more voids or more pores. So that increase in strength will be more visible in this type of concrete as compared to the concrete which initially have a higher strength. Initially have a higher strength means its particle packing will be much compact as compared to lower strength concrete in initial stages. So that increase in strength, it won't be that much of visible, or it won't be if we talk about percentage increase, that percentage increase will not be as much as in lower strength concrete. So from mainly for triaxial loading we will develop a more circles. So I think in mechanics you have studied about how to draw more circles and all. So this is, if we say this is shear versus tension, we will always draw in that way, and this will be your rupture mod envelope. Your different loading will be in terms of your semicircles, and the points joining all these three circles will give us the rupture envelope or the curve. Okay. So now other thing is that when we are talking about stress strain curve only, so this is giving me modulus of elasticity, rupture and all those things. The area below this curve, it will give us it will tell us about the toughness of our concrete. So toughness means which is indirectly proportional to the ductility of the concrete system. So more the area, more the area under the curve, more will be the toughness, more will be the ductility, and we can say lesser will be the strength value. So if here itself you see, if you have a curve like this and you have a curve like this, you have area under the curve in this way, so that area is less than this area. So more area means more toughness but lesser strength, and less area means more strength but lesser ductility or lesser toughness value. So other thing is, when we are making any new concrete, what should be the methodology that should be followed to study about it or to see if our concrete system is good for our construction or not. So if we see anything, we will characterize it in three ways. First is fresh concrete property, hardened concrete properties, and then is long term or shrinkage properties. So fresh properties, we have studied all the fresh properties in our last week thing: slump cone, VB consistency, inverted slump cone, and then if we are adding super plasticizer, what all, marsh cone test, all those things that will be giving us the fresh concrete properties. In hardened concrete properties, as we studied today, mechanical and durability. Mechanical, strength, toughness, impact resistance. In durability, we will mainly discuss about permeability, or it can be corrosion resistance also. And then about shrinkage. In shrinkage, we have 5 type of shrinkage. So we are dividing in 2 stages: earlier shrinkage, that is plastic shrinkage, which will mainly occur within one day because of improper curing and all. And then long term, we have free shrinkage, restrain, residual stress. So all these things it will be coming in the next week when we will talk about shrinkage and creep in depth. So this is one thing which is being taught about in class about the experimental study in at IIT Madras. So in that thing, we are limiting our study to the high strength concrete mix, where we are this is our concrete mix. We are having a low water cement ratio, adding silica fume, and aggregate sizes maximum 20 mm, and this is our mixed ratio 1 is to 2.505 is to 3.09. 1 is cement or binder, 2.05 fine aggregates, 3.09 coarse aggregates, with a water cement ratio of 0.4. So fine to coarse aggregate ratio is 0.65, and we are adding super plasticizer at a concentration of 2.5%. So now further we are using different fibers in this high strength concrete mix. So 4 type of fibers are used. So this is type of hooked fibers. So it look like a stapler pen. So it's called as hooked fibers. Other is, this is polypropylene. So this is a kind of what's say not metal, it's not a metal, it's a different type of fibers. Other thing is polyester fibers, so it will be like a powder kind of thing. And lastly, glass fibers. So these are glass fibers which are used. So what are the then these are the different type of fibers, and what should be the properties of these fibers, that is all given in lecture. You can see like a table is given. So first thing which we measure is flexure toughness. So in flexure toughness, if we are taking a beam, let's say this is a beam, and we are applying a loading at, we have 2 type of flexure testing in concrete: 3-point and 4-point loading. So I think you might have studied about those type of loading. So this is your 3-point loading, and in 4-point loading, what will happen? So in 4-point loading, we are giving 2 loading addition from top. So what will happen in this case? There will be crack will be sudden. In this case, you are uniformly distributing your loading, so you will have a better result in 4-point loading system as compared to 3-point loading. So here also is showing this is a 4-point loading, 2 points here and 2 will be here. So this is a 4-point loading system, and then we are adding LVDT to measure the displacement along at every point of testing. So this is a machine which is already available in our IIT Madras. So this is your testing condition, concrete loading condition, 2 bottom and 2 top. So 2 bottom and 2 top, and these are the results with different type of what to say, different type of fibers. So if you see here, this is your normal concrete with no fibers, and with the addition of fiber, what is happening, your peak loading condition is increasing, or your strength value is increasing, and with different type of fibers your post peak behavior is changing. So if you talk about first type of fiber, HST1. So which one is HST1? Let me double check. So HST1 is your hooked steel. So your steel one. So when you are adding your steel fiber, at that point of view you can see you have a very good post peak behavior, but as compared to your other type of fibers. So if you are using steel fiber or metallic fiber as compared to other fibers, your metallic fiber will have a good post peak behavior, but your, in that case your strength values not much higher. So this is your typical load deflection plot. Other thing is your flexure strength variation. So strength versus dosage of fibers. So dosage of non-metallic fiber and dosage of non-metallic fiber and dosage of steel fibers, increasing and decreasing in a way. So you can see how your flexure strength will change. If you talk about plain concrete, your flexure strength is approximately 5 MPa, but with addition of any fibers, your initial or your at lower dosage itself you have a better flexure strength as compared to your plain concrete. And this is how with different fibers it's changing. So it's telling about your steel fiber concrete. So that steel fiber concrete, I can't see the curve, so it is approximately similar to your pink curve. So steel plus your red one will be almost similar to your pink one. Other thing is how your flexure toughness vary. So what was the toughness? Toughness is area under the curve. So if you see here, your plain concrete is failing here itself, so area under the curve is very low, so your toughness value will be very low in this case. But if you are talking about different fibers, with different fibers your area under the curve is very high, you have a good post peak behavior, right? So your initial value itself will be very high. However, if you are increasing your non-metallic fiber dosages or decreasing your steel fiber dosages, your flexure toughness will start decreasing. Other type of testing which we are doing is, we talk about three testing: flexure, compression and impact. So this is your compressive toughness test setup. In this case we are not using a concrete cube, we are using a concrete cylinder of 100 by 200 mm, and this is how your curve will look like, load versus deformation curve with different type of fibers. So black curve which is going only till here, there is no much post peak behavior, that is your normal concrete, but with addition of different fiber you have a good post peak behavior. Same way stress strain curve of high density concrete, this is your stress strain curve. So with different type of fibers how it is changing, and same way here also similar kind of curves you can see with different type of fiber or different type of fiber concentration. Lastly, it is modulus of elasticity for high density concrete. So if you see here how your modulus of elasticity is changing for different type of concrete system. So for M20 concrete, for M40 concrete, how it is changing. So that's all you might have studied in this week 9 about the hardened properties of the concrete system. So there is not much about the durability study here, but I think we have covered those few of the durability things in previous lecture, and in details we will talk about it in the upcoming weeks. So if you have any doubt in the slides provided, please ask, otherwise we will see the question and answer for this week. You can post your question in chat box also. Okay, if there are no doubts, then we will see the questions. So the first question is state true or false. Higher the granular content in the concrete, higher the stiffness of the system. True or false?
The answer for this question is type F.
True.
True.
Low
Correct.
high
True.
temperature.
Correct.
That's why it has
The micro cracks in the ITZ opens or closes during compression testing of concrete, whereas during tensile strength they
B.
B. Correct. So during, as we were talking about fully, that during compression we are applying load from all direction and reducing the voids or reducing the cracks in the ITZ area, and during tensile we will open those cracks more. So answer is B. Next question is, cover concrete governs the concrete dash, whereas the core concrete governs the dash. Durability or strength?
A and B.
A.
Let's have it, Thomas.
Yeah. So if this is our any beam or something, we have
मैम मैंने कॉल प्रैक्टिकल ऑलरेडी है था
so if this is our any beam and we have stirrups here, so mostly our concrete will be affecting the corrosion problem. So cover concrete will governs the durability, and our core concrete will provide the strength to the concrete system. According to St. Venant's principle,
मैंने
while
कॉल से
testing
लिखा कमल कलम कुछ कुछ भी ऐसे कलम
next question is, according to St. Venant's principle, while testing, the end effects are felt up to a distance equal to radius of cylinder, lateral dimension of specimen, double
Lateral
the
dimension of the specimen.
okay. So you are correct. When while testing, the end effects will be till the lateral dimension of your specimen. That's why we will put our LVDT at the corners.
Silica fumes strengthens the
Concrete strength decreases when tested under hydrostatic condition. True or false?
challenge. Right? Next question is on why does silica enhance early age? What is that? Is leading to
True.
early age
False.
strength.
So it's false actually. Under hydrostatic condition, your concrete strength will increase. Hydrostatic condition means under triaxial loading,
What is that?
your under triaxial compressive strength. What we are doing, we are applying pressure from all three sides or all six sides. In that case, our strength is actually increasing. Next question is the compression post peak behavior of concrete is brittle, elastic plastic, strain hardening, strain softening. So if this is the condition for concrete, which curve is being followed?
B.
B, elastic plastic,
Brittle.
brittle. Okay, so in concrete mostly after
A.
you
A.
reach, correct, after you reach your peak position it will suddenly come down. Okay, for normal concrete it should be brittle, but when we are adding some fibers to it, it will have a strain softening, but here it is asked about only concrete, so it will be brittle in condition. The ability to take more strain by the application of additional stresses beyond the yield point is known as brittle, elastic plastic, strain hardening, or strain softening.
You can type your answer and jump on that also fine.
What do you think will be the answer?
Okay, this hydration, hydrated cement, control, fine. Somewhat
C.
incorrect, but let's
C,
see.
okay.
Answer exact in the tense situation.
Correct.
Fine.
So even after you reach the peak point, if you keep on applying additional stress and it's able to take more strain, that curve is called a strain hardening curve. Displacement control testing
Bunker.
can capture the post peak behavior. True or false? So we have seen two type of models in post peak thing.
True.
True, correct. So in those models we have seen one displacement type model also.
हाँ लिखी ले
Choose the curve corresponding to the fiber reinforced concrete. A or B?
B.
B.
B, correct. So in fiber reinforced concrete we will have a good post peak behavior as compared to our normal concrete system. A perfect compression fracture zone of pure compression shows crack dash perpendicular to the loading condition, parallel to the loading condition, at an angle 45 degree to loading condition. In case of pure compression, if you see from this figure,
perpendicular
Perpendicular to loading X direct.
perpendicular
Parallel to the loading.
parallel, see, loading condition is in this way and our failure planes are also in this direction. So in perfect compression it is parallel to the
B.
loading
B. B.
condition.
B.
Okay. Compared to uniaxial compression, at a state of triaxial compression, concrete strength will increase, decrease, or does not changes.
Increase.
Correct. Area under the complete stress strain curve is termed as stiffness, toughness, thixotropy, or flexibility.
stiffness
Stiffness.
Stiffness, okay,
B.
yeah.
Yes.
It should be
Toughness.
toughness. So we talked about it. It is area under the stress strain curve will give us toughness, not stiff. Rupture failure is expected in the case of steel fiber, glass fiber, polypropylene fiber, or polyester fiber.
Glass fiber.
B.
P, glass fiber. Okay. Anybody else who thinks some other option is correct?
Oh,
So your answer is correct. In glass fiber only we will have rupture failure, or rupture failure means your material or your fiber will break, suddenly break. So it will happen mostly in types of glass fibers when you are reading glass fiber. Next question is, steel fibers are stiff and long, making them efficient in bridging microcracks and hence improving the strength. It is a true or false statement?
False.
False. Okay. Anybody else who think it's a true statement? Correct. So it's not the steel fibers which will bridge the microcracks or improve the strength. It will be mostly in polypropylene type of fibers. Which property of hardened concrete is directly linked to its pore structure? Air content, permeability, setting time, or workability?
B.
E, correct. First thing is we are talking about hardened concrete, and all three other three are actually not hardened concrete properties. They are mostly fresh property concretes, and permeability will give us about the pore structure of our system. Next question is, biaxial compression generally increases strength due to reduced Poisson effect, confinement effect, microcrack bridging, or air voids. So in compression, what will happen? Your because of confinement of your pore structure,
A.
reduce Poisson effect. No,
Biaxial compressor. No.
it will be mostly confinement. We are talking about increasing strength in biaxial compression. So what is happening? Your pore size is decreasing, or your concrete is become more confined in the particular given area. Microcrack bridging will happen in case of triaxial compression. Which property of aggregate most strongly influences the strength? Roughness and grading, shape, specific gravity, or porosity?
C.
Specific
C.
gravity.
C.
Actually, all the properties will affect the
A.
strength. Yeah. So it is asking most strongly affect the strength property. It will be actually roughness and grading, because it will affect your ITZ area, your roughness and grading of your aggregate. And grading, if it is a well graded concrete, that means it will be more compact structure as compared to your poorly graded material. So answer will be roughness and grading. Which experimental method measures impact toughness of fiber reinforced concrete? Drop weight test, ultrasonic pulse velocity, split tensile, or resonant frequency?
A. Drop test.
Drop weight test.
Drop weight test.
Correct. So for impact, same way as we do for the aggregates, we have drop weight test for the concrete also. Use of hooked steel fibers in pavements will primarily improve setting time, toughness, shrinkage cracking, or heat of hydration in pavements.
C.
C. Shrinkage cracking.
B.
D. Heat
Either
of
B.
either B or C. Yeah. So normally if we talk about hood steel fibers, It will help you to improve your shrinkage cracking as well as your flexure toughness, but primarily it will be affecting your flexure toughness value, because if you remember that curve and all, mostly it will affect your toughness value. When steel aggregate is used in heavyweight concrete, modulus of elasticity will decrease, will be same, will increase, or will remain unchanged
So why, what is the role of
using steel aggregates.
A.
C.
C, correct. So if you are using steel aggregates in heavyweight concrete, your modulus of elasticity will actually increase. A dam foundation concrete requires resistance against alkali silica reaction. Which preventive method is best? Using reactive aggregates, low alkali cement, increasing curing temperature, or using higher water cement ratio? So I think SR will be in next to next lecture, but if you know anyone,
A.
B.
A.
B.
A, B. So main preventive measure, best preventive measure is using low alkali cement. So B will be correct option. Last question. In earthquake prone zones, the most desirable property of concrete is having high compressive strength, high toughness, low heat of hydration, or higher modulus of elasticity.
B.
C.
B, C. Okay. So even if you have low heat, so if we talk about desirable property of concrete in a earthquake zone area, then we will talk about its hardened properties mostly. So we are not concerned about heat of hydration. If we talk about hardened property, it should have higher toughness or higher ductility as compared to its higher modulus. So B is the correct option. So that's all for this week. If you guys have any doubt, please ask.
no effect, and the coarser particles in the soil. And for how the particles perform, what will happen is the fine essence are used to control
If you guys have no doubt, you can leave the class also.
property of your component.
Wait for 5-10 minutes. If you have any doubts, you can ask.
Thank you, ma'am.
Thank you.
Okay, answer B is coming. See the answer. Answer B is correct. Fine particles will propose obviously. The more the fine particles are, the more surface area they have, more surface area they can more reactions cement and ensure finer particles leave the should right. Next question is on why is the fly ash important for concrete? Prevent color variation, ensure consistent setting time, capability or ability as well. This is the hydration rate control. While the uniformity is required. Because if your fly ash source are changing, the properties of fly ash, which could be a problem. What is that problem? Why is it the question? So it's straightforward, it's easy to ensure consistency and setting time. State is controlled by the chemical composition. Hence, we require constant chemical composition and the bottom cycle also to ensure these properties are met. The next question is on what is the effect of high pressure fly ash on the early age properties. Reduces the hydration, improves value chain through the self-cementing reaction, and increases the shrinkage only, and weakens the class C class level class C the fly ash class C is having high calcium content. What is the advantage of having high calcium content when it comes to early age concrete properties? Again, the answer, let's see, the answer is correct. Improve the early stage to the cell cementing reaction of this because they already present calcium is there. And that can be itself.
If there are no doubts, then I will close the class for today. Thank you all for joining.